to School of DAPPS. On this channel, we turn aspiring developers into skilled blockchain experts across various network and technologies. In today's video, we are going to build a counter smart contract on the NEAR blockchain. This contract will act like a simple counter. Users will be able to increase, decrease, or reset a number. It's a basic example, but the main goal is to help you understand how to write smart contract on NEAR blockchain. So first, we will start by bringing in the tools or the modules or the library we need. To do that, we'll import the necessary items from the NEAR SDK. We use the keyword use, followed by the library name NEAR SDK, then the path operator, and finally the tools we need inside a curly bracket, which simply tells NEAR that we are going to use its SDK tools. The log is for printing messages to the blockchain logs, and the NEAR is to define smart contract components. Let's define our contract. First, let's write a macro attribute that tells NEAR that this struct will hold the contract state. The state is where we store the value of our counter. To do that, we will use a macro attribute. We write a hash, then square bracket, and inside the square bracket we write NEAR, followed by a parenthesis. Inside the parenthesis, we specify the purpose of the macro, in this case contract state. This holds the state of our contract, which in this case is the counter value. Next, we need a macro attribute that allows us to create a new contract instance with default value. This is also done using the macro attribute. Just like the first one, we use the hash and the square bracket, but this time inside the square bracket we write derive, and inside the parentheses we write default. This macro enables us to create a new instance of our smart contract with default value, meaning the counter will start with a default value of 0. Now we write a struct using the struct keyword. The struct will represent the data we are storing in our smart contract, which is the counter value. Inside the struct, we will define one field called val, which will store the counter numbers. We specified that it's an integer of size 8, which is the type, meaning it's a small integer that can range from minus 128 to 127. We are going to write the smart contract logic that will allow users to interact with the counter. This function will let users increase, decrease, and reset the counter. Each of these functions is like a button you can press to change the number. So here's how we define the function. First, let's define an implementation block for our contract. To do this, we use the hash NEAR macro attribute. This macro tells NEAR that we are about to implement the function for the counter struct, and that the following block of code will be the implementation for the counter contract. So we write impl counter, which stands for implementation block. Now let's write the first function, which we'll name get number function. This function will allow the users to view the current counter value. It doesn't change anything. It just returns the current value stored in the val field, which we define within the counter struct. To define the function, we use the keyword pub fn syntax. The pub keyword makes the function public, meaning accessible outside the contract, and the fn defines a function in a Rust programming language. We will pass in a reference of self as a parameter. This allows the function to borrow struct without taking ownership of it. Then return an integer of size 8. Inside the block, we will return the current counter value. val stored in the counter struct. Let's write the increment function. Public fun increment. We will pass in a mutable reference of self and a number that is optional, which is of a type integer of size 8. This function increases the counter by a specific number. If no number is provided or passed as argument, it defaults to adding 1, increasing the counter by 1. Then we add the number to the counter. So we write self.var plus equal number unwrap, or in a, then we write 1 within the parentheses. Then we will log out the updated counter value to the blockchain. Let's write the decrement function. This function decreases the counter by a specific number. If no number is provided, it defaults to subtracting 1. Pub fn decrement, we will pass in a mutable reference of self and a number that is optional, which is of a type integer of 8, size 8. Then we'll subtract the number from the counter. So if no number is passed, it will subtract 1 from the counter. Then we will log out the updated counter value to the blockchain. Lastly, let's write the reset function. Pub fn reset. We will pass in a mutable reference of self. These functions will set the counter back to 0. Then we will assign 0 to the val feed in the counter struct. Then we will log out the updated counter value to the blockchain. Each of these functions helps user interact with the counter state, changing or reading the counter as needed, and importantly, each function logs the actions to the blockchain for transparency and traceability. Now that we have finished writing our contract logic, we want to make sure it works as expected. So we'll write a test for the contract. Testing is very important because it helps us catch bugs before deploying the contract to the blockchain. NEAR support unit tests using ROP's built-in testing framework. To start writing tests, we first write a special macro that ensure our test only runs in a right environment, that is not on the actual blockchain run time, WAMs, but in a normal Rust testing environment. We do this using the CFG macro. CFG macro stands for configuration. All test not target architecture WAMs 32. This attribute only compile and runs the following block if we are running tests and not targeting the WebAssembly. Basically, this tells us to ignore this block when building for the blockchain. Now let's open the test module using a mode keyword and give it a name. We will name it test, then open it with curly braces. Inside this module, we need to access the function and the struct we already defined in the main contract. So we need to import everything from the parent scope using the use keyword followed by the super keyword, then the part operator and then asterisk, which allows us to reuse the contract and call its method for testing purposes. Now let's start writing our test function. We will start each one by using a macro hash test that marks the function as a test. The fn keyword is to declare a function. We name it increment. Let's declare a mutable variable named contract and assign a new counter instance and start the value at 0. Then we will call increment function in the contract and pass none as an argument, which means we will increase the counter by default value of 1. Finally, we'll check that the value is now 1 using the assert equal method or macro. If the actual value is not 1, the test fails. Now let's write the second test function. Just like before, we start by using the test macro to tell us that this is a test function. Then we use the fn keyword to declare a function, and we write the name of the function, in this case increment with point. Next, we will declare a mutable variable called contract and assign a new instance of the counter struct, starting the counter value at 0. We do that with this line of code. After that, we call the increment function on the contract, but this time instead of passing none, we'll pass in sum with 10, which means that we want to increase the counter by 10 instead of the default number, which is 1. Finally, we'll check whether the value of the counter is now equal to 10 using the assert equal macro. If the counter does not equal 10, the test will fail. In summary, the test confirms that when we explicitly provide an amount to increase the counter will correctly reflect the new value. Now, we are going to write another test function, but this time it is for decrement behavior. We start by marking the function with the test macro, then use the fn keyword. We will define the function and then use the fn keyword and name it decrement. Inside the function, we first create a mutable variable named contract and assign it a new instance of counter struct. We will start the counter value at 0. Next, we call the decrement function of the contract and pass in none as the argument. By passing none, we are telling the contract to decrease the counter using the default value, which is 1. Finally, we want to make sure the counter has decreased correctly, so we use the assert equal macro to check if the correct counter value is now -1. If it is something else, the test will fail. So this test confirms that when no value is passed to decrement function, the counter correctly subtract 1 from its current value. Now let's write a test that check whether the counter can be decreased by a specific value. Just like before, we start the function with the test macro to mark it as a test, then use the fn keyword and give the function a name, which is decrement with point. Inside the function, the first thing we do is create a mutable variable called contract, just like we have been doing before, and assign a new instance of the counter struct, starting the counter at 0. We call the decrement function of the contract and pass in sum 10 as the argument. This means we are explicitly asking the counter to go down by 10 instead of using the default value, which is 1. Finally, we will need to confirm that the counter actually decreased by 10 by using the assert equal macro to assert or check if the value is now -10. If not, the test will fail. So this test confirmed that we passed a specific number to decrement function like 10. The counter accurately subtracted the value and updated its state accordingly. Now we are going to test a slightly longer interactions where we increment the counter and then we set it back to 0 as always. We start by making this function as a test using the test macro, then define the function with fn and name it increment and reset. Inside the function, the first thing we do is create our contract instance. We declare a mutable reference called contract and initialize it with the counter value of 0. Next, we call the increment function on the of the contract and pass in none. This tells the contract to increase the counter by the default value of 1. Then immediately after incrementing, we call the reset function. This function sets the counter value back to 0. No matter what it was before, no matter the number it was before, it will set it back to 0. Finally, we verify that everything works as expected by checking our counter value using the assert equal macro to make sure that the current value is indeed 0. This test helps us confirm that the contract can both increment and reset correctly, and that reset truly clears out any previous value, restoring the counter back to its initial state. Now let's test what happens when the counter overflow. Overflow means we try to increase the counter beyond the maximum value that the integer of size 8 can hold. Remember, the maximum value that 8 can hold is 127. To catch this kind of issue, we use a special macro attribute called should panic. It goes right above our test function and tells Rust, hey, this test should crash. If it doesn't crash, something is wrong. So yes, how we start the test. The test macro followed by the should panic macro. Then we define the test function and give it a descriptive name called panic on overflow. Inside the function, we first set up our contract as usual. We write the immutable reference called contract and initialize it with a counter of 127. With a counter value of 127, which is the highest value allowed by the integer of size 8. Next, we try to increment the counter with none as the input. Since none defaults to 1, this line is trying to push the value from 128 to 127 to 128, which is not allowed for an integer of size 8. Because the value is out of range, the contract will crash or panic and the test will pass, but only if the panic happens as expected. So this test makes sure our contract doesn't silently break when the contract goes above its maximum limit. It forces the contract to crash, and that's exactly what we want in this case. Now we are going to test what happens when the counter underflow. Underflow is the opposite of overflow. It's when we try to decrease a value that's already at its lowest possible number. Since we are using integer of size 8, the lowest value it can store is minus 128. To check that our contract behaves properly in this scenario, we write a test function and use the should panic macro. Then we define the test function and name it something descriptive like panic on underflow. Inside the function body, we create a new contract instance with a counter already set to 128. This is the maximum possible value for integer of size 8. So we are at the edge. Then we try to decrease the counter using the decrement method and pass the none as the argument. Since none defaults to subtracting 1, this line is trying to go from minus 128 to minus 129, which is not allowed. The action will cause the contract to panic, and the test will pass because we expect it to panic. This test is important because it helps us catch potential bugs where value goes out of range. We are making sure the contract won't behave unexpectedly when someone's tried to go beyond the maximum limit, the minimum limit rather. After running cargo test on my terminal, this is the result of the test. All right, you have come to the end of the lesson. If you've gained value in this lesson, don't forget to like, comment, and subscribe to School of Tab for more easy to understand blockchain tutorial. Do you have a topic you want us to cover next? Drop it in the comments section. See you in the next video. Future blockchain champions.